Okay, so this lecture or this series of lectures is going to be about data that have outliers or other bad data. Okay, so what do we mean by outliers? So consider our usual kind of data set. We have xi and yi, both real numbers. And let's say we plot x versus y like so, and these black dots are the data, and we have black dots that are here, right? So all over the place, in addition to what seems to be the primary trend in the data. Usually, these kinds of data points might be called outlier data, right? So by definition, outlier data is data that somehow does not correspond to the trends in your data or trends in most of the rest of the data or the distribution of most of the rest of the data, right? So that's what we mean by an outlier. So it's sort of a subjective thing. Of course, one can make an objective definition in particular cases, but in general, there is not a uniformly accepted definition of what an outlier is. There's not a single specific mathematical definition of an outlier. People use different definitions, and the definition may depend on the context, right? But outliers would just be something that is different, substantially different, perhaps, very crudely speaking. Okay, so that's outliers. Now, how do you go about finding what the outliers are? What are a few heuristic methods for finding outliers? Okay, so here's idea number one. Let's say motivated by data that looks like this. We will very soon see a MATLAB implementation of this that we can walk through. So let's say again we are given data xi comma yi. We want to determine the data indices j such that xj or yj are too far from the mean of the respective variable, right? So this is one way of finding outliers, right? So you have a list of xi and yi, and then you look at xi and yi, find the mean, and then see are there xi or yi that are too far away from the mean by some definition, right? So how do you define too far? Let's look at y. Um, let's first find the mean of yi, like mean of all the yi's, and let's call that mu y. And let's define the standard deviation of yi, which tells us something about how spread out the data is, right? So the mean is what's called a measure of central tendency, like sort of the typical center point of the distribution. And the standard deviation is a measure of uh, the overall distribution, right? The spread of the distribution. Okay, so once you've measured the mean and the standard deviation, or computed the mean and the standard deviation, you can compute something called the z-score for each data point. What is the z-score for each data point? It's the data point minus the mean divided by the standard deviation, right? So it is a measure of how many standard deviations is yi from the mean of yi, all yi, okay? So how many standard deviation away from the mean is your data point? And you look at that value for each data point, and if it's too far away, then you call that an outlier. That's the basic idea. So it's kind of a normalized distance from the mean, okay? Normalized distance from the mean. And it's typical to, depending on the context, eliminate all data points that have z greater than 2. What does z greater than 2 mean? Or absolute value of z is what we mean here. Absolute value of z greater than 2 means that your data point is at least 2 standard deviations away from your mean. Or z greater than 1 would be 1 standard deviation away, right? It's even more common if you have well-behaved data. It's even more common to use z greater than 3, which is 3 standard deviation away. And in manufacturing context, you might have heard the term Six Sigma, and that's dealing with data or objects that are 6 standard deviations away, right? Okay, so it's actually a measure of this distance from the mean. Okay, So that would be one way. So figuring out which y's are a few standard deviations away from the mean and throwing them out would be one way to eliminate outliers. Now, this way might work if the data has some good properties, like normally distributed, but this could have multiple problems. Okay, so here's problem number one. Let's say you have x versus y data that looks like this, and these 2 points seem like outliers visually to us, right? So it looks like outliers, but unfortunately, these 2 points will not be categorized as outliers by this algorithm, because if you look at the range of y, it goes from here to here. So these 2 points are actually pretty close to the center of the y distribution. So these 2 points will not be classified as outliers. So just using the output y in determining what the outliers are can be misleading, because you can have what we should call outliers not be captured by that procedure, right? So this will not be captured because, well, if you had a point out here or out here, then that will be 2 or 3 standard deviations away from the y, from the y's mean. But here we are actually pretty close to the mean, which is going to be here, right? These 2 points are probably within 1 standard deviation of the mean. Okay, so that's problem number one with this method. Problem number two is that this method relies on computing means and standard deviations. Means and standard deviations are themselves actually susceptible to outliers. If you had a crazy outlier somewhere, like very far away, right? So way outside the screen, let's say you have a data point way here, then really, really far away from the rest of the data set, then the mean of the data will actually be pretty close to this outlier. So the outlier will pull the data completely away from most of the other data. That's possible. And then the standard deviation is also going to be incredibly large because of the outlier, right? So just using the mean and the standard deviation might itself be a problematic approach for determining what the outliers are. So just to indicate why the mean is actually a bad way to detect outliers, if you have outliers, is like I usually give this example. Imagine a room full of people, um, and they're regular folk, and they have some personal wealth, let's say, and they would have a particular mean and standard deviation wealth, um, that is typical of a typical person, perhaps. But then, let's say you bring in Bill Gates or some incredibly rich person into the room. The mean now of the uh, wealth of the people in the room is now going to be in the billions, if there are 10 people in the room, let's say, which is completely unrepresentative of the typical quantity, right? Which is what we want to capture with the mean. Similarly, the standard deviations will be in the billions as well. So just using means is very susceptible to, is a bad approach to doing anything to do with outliers. So, which you can actually fix by using other quantities that are like the mean but are more robust to outliers. Okay, so this particular problem can be fixed by using medians and percentiles. So instead of the mean, you would use medians. And instead of saying 2 standard deviations away, 3 standard deviations away, or whatever, you would speak in terms of percentiles. Okay. So how does this work? So what does a percentile mean? Percentile, so median is actually the 50th percentile. Median is, if you have a bunch of numbers, it is the middlemost number. Or if you have a median, 50% of the data is below the median, 50% of the data is above the median. Percentile is just a generalization of that idea, as I'm sure all of you know. If the 80th percentile means that 20% of the data is above the 80th percentile, and 80% of the data is below the 80th percentile, right? If you have 100 data points, 20 data points will be above the 80th percentile. I don't know, 79 or 80 data points will be below the 80th percentile. Okay, so we use those kinds of quantities. And notice that the median, for instance, is robust to someone like Bill Gates entering the room, right? So if you have 10 people and let's say they all have some average wealth equal, let's say, and Bill Gates comes into the room, the median will not change because the middlemost value of the wealth in the room will not have changed at all, or will change very little. It'll go from um, one person to the next person as opposed to shift incredibly by billions. Okay, so so we can use medians and percentiles, and using medians and percentiles to eliminate outliers. There is a term for that procedure. It's called Winsorizing, presumably related to the name of a person that suggested this method. Okay, so how do you do this? You, let's say, sort the y values from minimum to maximum, and then remove, let's say, the top 5% of the data and the bottom 5% of the data and call them outliers, and just keep um, data between the 5th percentile and the 95th percentile. Okay, so you're basically keeping 90% of the data. That would be called Winsorizing or things like that. A bit more common is keeping 95% of the data, which is actually going between 2.5 percentile and 97.5th percentile of the data. Okay, and that works pretty well. Okay, so this is the way of fixing um, the problems given rise by using means and standard deviations, because means and standard deviations can be affected a lot by having outliers themselves, right? But it doesn't quite fix this problem, right? So where your data points are actually pretty close to the mean or the median already, but we would like to be able to find a method that eliminates this, right? So how do you do that? The way you do that is actually take the data and then actually fit a line or some pattern, some model through the data, and then see what the error is for the various data points for the model, right? And then use the error to actually eliminate these data points, rather than base what an outlier is based on your y value. You would base it on your error from some model. Okay, so let me talk about that in the next short video.